So the title was supposed to be a challenge. We teach our students, unless you're reorthogonalizing, you don't want to use classical Gram-Schmidt. Okay, so this is one way to write the classical Gram-Schmidt algorithm. I'll use this notation in some of the other algorithms that I'll show later. So here I'm using a MATLAB-like concatenation of the columns of Q and R down at the bottom. But we typically do this in place in A, so Q overwrites A. We don't have extra storage for Q, but we have a matrix vector product that's growing larger at each step. And then this S vector is just the orthogonal, the projection of A sub j onto the orthogonal complement of the previous A sub j's. Classical Gram-Schmidt kind of famously falls apart when you have this row which is small, and then any errors that you've made in here get magnified when you go on to the next step, which tends to ruin the orthogonality of the Q matrix, and it kind of snowballs from there. Oh, before I do that, I wanted to get kind of cute and show a puzzle that I give my students. And so there's a silly programming thing here in lines 2 and 3, but it allows me to ask my students, change one character in this code to change this from MGS to modified Gram-Schmidt to classical Gram-Schmidt, or vice versa. So I think the first question is this, as stated, classical Gram-Schmidt or modified Gram-Schmidt? And then how do I change it from one to the other with just changing a single character in the code? So it's kind of a phenotype versus genotype thing, that classical and modified Gram-Schmidt give very different results as far as the orthogonality of Q goes. But if you write the modified Gram-Schmidt in the column form, which is done here, then you can change from one to the other with just the change of one character. So they're closely related, even if they behave quite differently. Okay, so in real arithmetic, in exact arithmetic, we get this QR factorization. Q transpose Q is the identity, and R is upper triangular. In finite precision, we still have a truly upper triangular matrix R, but I can't say that Q has orthonormal columns anymore. And I have this kind of residual error that talks about, that measures the distance between A and Q times R. So I'm not going to use bars over the computed Q and the computed R like it's typically done for this talk. We'll just let Q and R be the computed factors. And for classical Gram-Schmidt, you get a very nice error bound on the residual. And so this theorem is the main result of the talk. I'll briefly sketch this theorem in the next couple slides, and then apply the idea that this theorem gives me to generating a few algorithms that we can talk about. But basically, I can bound the orthogonality of Q much like the modified Gram-Schmidt bound on the orthogonality of Q. In here, I'm giving a Frobenius norm of R, and typically that's given as a 2 norm of A. So that's just to make this talk be more simple to understand. And so the hypothesis here is that once I do my QR factorization, and then I look back at my triangular factor R, if it's column diagonally dominant, then I have an orthogonal Q. As it stands, that's this posteriori hypothesis might be hard to implement. I think the fastest way to find it, if A equals QR gives you an R that's column diagonally dominant, would be to do some kind of Cholesky factorization of A transpose A. and you could check the Cholesky factor. That'd be a little bit faster than doing the Gram-Schmidt. But this idea of R being column diagonally dominant comes back to if R in the one norm is less than or equal to this rho factor, which sits on the diagonal of R, but is the normalization of the projection of AJ. And I was just here reminding people what I mean by the Frobenius condition number. R is squares, so it makes sense in this case. And then again, this doesn't affect our code or our software at all, but for the purpose of the talk, I'm going to assume that the columns of A have unit 2 norms. And I could do a QR factorization of the scaled version of A and recover the QR factorization of the original A this way. And so, and I can make the error analysis slightly cleaner here if the columns of A have unit 2 norm, because this factor, the norm of A and the 2 norm, was just standing in for the largest column, the largest 2 norm of the column of A. So, I mean, one advantage to this assumption of scaling is that it simplifies this error analysis a little bit. So this is the guy we're after. I want to find a bound on how far Q is from having orthonormal columns. And we just noticed that if I subtract R from Q transpose A, in exact arithmetic, this will be 0. And I'm just dropping in our computed factorization of A here. And I get this I minus Q transpose Q times R. And this is where I'm going to try to get to the norm of E, is through the norm of I minus E times R. Okay, and then we notice that in classical Gram-Schmidt, the strict upper triangle of E transpose R is Q transpose F. In other words, that's the way R, the strict upper triangle of R is defined. And so we're going to use R transpose E just because of a nice norm result to bound E. And so in 2005, Giraud and Longo, and I'm not sure if I'm pronouncing the names correctly, proved that the classical Gram-Schmidt had loss of orthogonality in Q that was proportional to the square of the condition norm of A. And people for 60 or more years were trying to find a result like this. And our computations pretty much confirmed that it has to be this. But nobody came up with a proof for this. It turned out that Giraud's original proof had some mistakes in it, but Smaktunovitz fixed it in the next year. I would have loved to have been a fly on the wall in some meetings during 2005. They used, rather than what I'm going to use E transpose R or its transpose. They used R transpose ER, and you can see why they get a condition number squared of A when we get to that slide in my analysis. But I have this very severe restriction on R, that the one norm of the upper triangular columns of R are less than or equal to the diagonal. Does this make sense? Can you think of questions? Yeah.
Can you repeat what is SUV?
Oh, I'm sorry. Yeah, strict upper triangle. Yeah, so like TRIU A comma minus 1 or comma 1 in MATLAB. Yeah. But these results, like I said here, were a long time coming. Okay, so here's the brief outline of the proof. So after that K plus first step, I didn't want to put all the subscripts, but this this is R sub k, and this is little r sub k, and this is rho sub k. And here's our hypothesis then that the one norm of R is less than or equal to rho. And so if I compute Q or I minus QK plus 1 transpose QK plus 1, I get this kind of structure. And the main terms here, E and E times R over rho, are the price we pay in this step for the loss of orthogonality in Q from in the previous steps. But these terms with the little f and rho times Q transpose Q just come from rounding errors that were made in this step. And this condition up here, along with the columns of A having norm 2 norm 1, says that this rho that we're dividing by here and here can't be smaller than 1 over the square root of 2. So I cannot have that tremendous loss of orthogonality in classical Gram-Schmidt that you sometimes see, or that you often see, I should say. So I'm just taking this matrix RK plus 1 transpose times this, and it has this triangular structure based on the errors from the orthogonality of Q. And then I'm just ignoring this piece for right now. I'm calling it local error. But again, this G corresponds to these guys here, and they're just giving us the rounding errors that we made in the current step. And they're kind of, in this sense, then is related to the original residual in this way. And the square root of 2 just comes from the fact that this rho could be as small as the square root of 2. Okay, so I just repeated that in the previous slide. That was the last thing. And just so you had it in your mind for the next bit, I put it up here again without the G, without the local errors. And so this is just one column. So this R transpose is K by K, and this whole matrix is K plus 1 by K plus 1. So I have a column here and a scalar here in the 2-2 position. And this condition that we have on our theorem says that the largest this could be is this mixed induced norm, where I'm maximizing over the 1 norm and the 2 norm. And so I'm calling that the R21 mixed norm. People in like lasso optimization and stuff use this notation that says this would be R transpose E, 1 arrow towards 2. And I've seen the arrow go to the right or the left. Golub and Van Loan and Horn and Johnson and several other people would call this the 1,2 norm. But here's the definition that I'm using, whatever I decide to call it here. And this is one of those mixed induced norms that we have an easy computational result for. Some of them are NP hard to compute, but this 2-1 norm is just the maximum of the 2 norm of the columns. And this final scalar down here turns out to be just the square of the length. Well, this is the Pythagorean theorem here, right? With some rounding errors that we made when we computed S and the length of S and so forth. This turns out to be a key to the error that Giraud made in the 2005 paper, and Smaktunovitz fixed by noticing that if we compute this rho squared as the length of A squared minus the length of R squared, then this has to be small. And generally speaking, the loss of orthogonality in Q can make this large. And so that's why the final version that classical Gram-Schmidt has errors proportional to the square of the condition number of R comes from computing it in this Pythagorean sense. And Erin talked about that in a recent paper that she published on block Gram-Schmidts, and noticed this Pythagorean version. For us, whether you use the length of R, the length of S computed directly as the norm of S or through this Pythagorean way, it doesn't make very much difference, because R can't be, rho squared can't be small. And so in our code, we've used both the Pythagorean way and the straightforward way of computing rho, and it doesn't make any difference. So this result up here says that the 2-1 norm of R transpose E size k plus 1, and that is this. And so when I look at the next step, I have the orthogonality error no bigger than the orthogonality error that I had previously. So this allows for easy induction that says the norm of R transpose E can't grow more than the local error at each step. And so here's a real simple one. Way to see that is that if we just look at the Frobenius norms, then I can insert an R and an R inverse here. And then the Frobenius norm is submultiplicative, so I can pull out that. Here's the R transpose E that we spent so much time trying to bound. I'm looking at the Frobenius norm of R transpose E, and what I have is the largest norm of R transpose E, so I can multiply that by the square root of n and get this, the Frobenius norm, a bound on the Frobenius norm. And then, so there's the condition number of R and the Frobenius norm and our bound.
So E, what is E here, EK?
So, oh, that's I minus Q transpose Q.
I'm not sure the measure is naturally RK transpose EK. RK is like R by R, and then EK is N by R, right?
No, EK is square. It's K by K. Yeah, I'm just looking at, I'm just looking, there's our EK right there. Our EN right there, right? And then I made it more confusing by dropping the subscripts here. So I thought it was way too busy to have RK and little rk, the subscripts on those. But EK is this guy, so it's K by 1 by K by 1.
Actually, just want to make a small comment here.
Yeah.
So the 2-1 norm. So nowadays, I think so in the machine learning literature, the 2-1 norm actually means that for a matrix, we compute the 2 norm for each column.
Right.
So then we get a row vector and then take the 1 norm. So
which is the maximum, of the Q norms, right?
So in the machine learning language, where actually this is the 2 infinity norm, because you're taking the max rather than the sum.
I'm taking but you compute the 2 norms of the columns, yeah, and put them in a row vector, and then you compute the infinity norm of that, right? Yep. And then what do you call that?
No,
because that's what this is.
What I'm saying is that so when a machine learning person is seeing the 2-1 norm, rather than taking the max, it takes the sum.
The sum. Okay.
It's different language.
Right. And that's the 1 goes to 2 norm, or the 2 goes to 1 norm in the machine learning context. Okay. So here in the domain space, we're looking at the 1 norm, and then in the range space, we're looking at the 2 norm. Other comments? Yeah, I wrestled with this because this is going against Goldman Van Loan, it's going against Charles Johnson, Horn and Johnson. I think Nick Hyam uses 1-2 instead of 2-1. But if I say a matrix is M by N, I think of the right superscript or subscript being the domain and the left being the range. So anyway, we're arguing about something we don't need to. Okay. So there's my sketch of the proof. So we have this algorithm so that if after you're done with it, you look at R and it's this column diagonally dominant matrix, then you can be confident in the Q. And so what I want to do now is look how we can use that I'm calling it a reorthogonalization criteria, but I'm not going to reorthogonalize just because of the title of the talk. I have code where I do actually reorthogonalize, but I didn't want that to be part of this. So what I'm trying to describe here is just a general classical Gram-Schmidt with a selective reorthogonalization. And so the idea is you go ahead and compute R and S and rho the way you would normally do at each Gram-Schmidt step. And so this jammed up one line of code is basically the classical Gram-Schmidt algorithm. But here you ask the question, should I reorthogonalize? Right? And if the answer is yes, I should reorthogonalize, then I just do this Gram-Schmidt process again. And then I update my R and update my rho. And this could be a while loop instead of a for loop. People have studied reorthogonalizing several times in case you wanted to get machine accuracy. There's famous history of just 2 times is enough. And Page and Bjork did some of the fundamental work on this stuff. But I'm just going to use this reorthogonalization criteria to decide whether to continue with the current block of a block QR factorization or start off with a new block in a block QR factorization. And so historically, this reorthogonalization criterion was looking at the 2 norm of R compared with the diagonal of the 2 norm of the upper triangular piece of R compared with the diagonal entry of R. And Langau and Girard, or Girard and Langau, oh, here I have it. Girard and Langau in 2013 showed with some clever counterexamples that if you're using the 2 norm of R here, it doesn't really matter what K you use, you can be in trouble with the loss of orthogonality of Q. So you can make this very restrictive, like K less than or equal to 1/2, and still significantly lose orthogonality in the columns of Q. And in 2003, Girard and Langau said, you should really be looking at the 1 norm of R. And they do say in their paper that it costs a lot more when you do this. You have to reorthogonalize much, much more often than with these 2 norm kind of criterion, but that at least you're guaranteed with modified Gram-Schmidt, the nearly orthogonal columns of Q. And so we're going to move this to the classical Gram-Schmidt using the theorem that we just looked at a second ago. And again, if I take L to be 1 here, then this is that column diagonal dominance in R that the theorem required. Okay, so I gave a reorthogonalization criterion, but we're not going to reorthogonalize. The idea is and I guess we'll see this as the next few slides come up, but I'm working on a classical Gram-Schmidt factorization of several columns of A. And I have to decide whether I'm going to say, okay, that's big enough for this block, or do I continue to enlarge this block based on this previous theorem? And this whole idea can be set in Erin Carson's, she had a paper just came out this year that kind of beautifully put all the well-known at least block Gram-Schmidt algorithms in one common framework. And the idea is that you have to do some kind of factorization of the current column of Q that you're in. And that's called an intra-orthogonalization or a muscle for the overall block algorithm. And then you have several alternatives also for what you might use in the block modified Gram-Schmidt or the block Gram-Schmidt step. So that's coming up in the next slide, so I'll get to it. And I do want to have show a caveat here is that the way these algorithms for the rest of the talk are going to go, I'm taking advantage of BLAS2, lots of matrix vector operations. But I mean, one of the beauties of the block Gram-Schmidt is that it's BLAS3, it's matrix multiplications, which in high performance computing centers can give lots of speed up. So when I'm doing a matrix product, I'm doing it column-wise, a bunch of matrix vector columns products, so that I can ask, given this new column, should I expand my block or should I start a new block? So so this is going to take some unpacking. So it's the standard input. I have an n by n matrix with full column rank. And here I'm getting output like the rank revealing QR factorization. So I have a permutation matrix here. And I've got a partial QR factorization for this first block. And then this is what's left over. And so we just do, this is a standard QR step for the first step. And here I do the jth QR classical Gram-Schmidt step. And here's where we ask, should we reorthogonalize or not? And instead of reorthogonalizing, we're just going to switch to a new block. In my code, L is set to 1. But if I pass this reorthogonalization step, then I'm going to increase the size of my block. So I'm going to add a column to the current Q1 and then update the R matrix also. But if I don't, I'm going to reject this S vector that I've computed up here. I'm not going to divide by row, and I'm going to update the R matrix. And so I get this collection of two matrices, Q1, which has, up to our theorem, orthonormal columns, and Q2, which I was told to reorthogonalize because I wasn't orthonormal enough. And so I just saved those. And so what this code up here does give us is just a partial QR factorization. And then what I did down here is if we just added, this is CGS reject here, and this is CGS reject here. So if we just added this recursive step here, then this would give us this QR factorization, AP equals QR.
Just replace the norm by 1.
I'm just replacing the norm by 1, and the K factor, I'm calling it L, and I'm letting it be 1 also. But yeah, all we're doing is replacing the 2 norm with the 1 norm of R in the reorthogonalization. And I do get a full permuted QR factorization. If I was in your code, you wouldn't want to call this as a recursion. You'd probably build a stack. Believe me, I've written it with recursion and I run out of memory when n is very big. But with a stack, it's not using very much extra memory. I should also say that I'm doing this in place. So I may say that Q1 is the Q matrix with this new vector appended, but really they're all being stored over the columns of A. So I'm not using, twice the memory that I have to. The point is that I've partitioned the columns of Q into two pieces. It'll allow me to describe this stuff later in a bit. I'm going to unpack this in the next 2 slides, so I'll ask for questions after that, and we can come back to this. The first thing I want to unpack is this is an old person's term. I don't know if people use psychologically upper triangular anymore. Do you remember that, Yusuf? Psychologically upper triangular? Anyway, here's. Yeah, right. There was morally too. Yeah. Okay, so this is what I mean by psychologically upper triangular. It just means that R is a permutation equivalent to a triangular matrix. So it has just as many zeros as an upper triangular matrix. They're just in weird spots. And this permutation matrix P that we had in our algorithm here or here can undo that and give this P transpose RP upper triangular form. And since Q has orthonormal columns and P is a permutation matrix, then this is a QR factorization of A, whatever letters I've used, right? And then there was this piece here that I brushed over very quickly. I need to update the rejected columns, the ones in Q2, by those subsequently accepted that were in Q1. So we have a bunch of columns of the original A matrix. I'm replacing them by columns of Q1 or Q2. And as this algorithm proceeds, what it does is it sweeps across the whole matrix, putting columns in either Q1, which is a collection of orthonormal columns, or Q2, a collection of rejected columns, right? So if I have a vector that was rejected and then later a vector that was accepted, that stored rejected vector never got orthogonalized against the later accepted vectors. And so this cleanup step is certainly necessary. And that's what I wanted to talk about in this slide here. Oh, so I should have had this slide up when I was just blabbing with waving my hands. So here are the accepted vectors. These guys we can assume are close to working precision orthonormal. And these are the guys that I've projected out columns of A, but I've decided to reject them because they were too close and we were worried about the rounding errors. And so each of these rejected vectors has associated with it a set of vectors over here whose indexes are strictly less than their index that need to be orthogonalized against the previous Qs. Does that make sense? So this QR1 is the first rejected vector. And it could be that I have a bunch of vectors here that were accepted before I got to this first rejected vector. It got rejected, and so was never I didn't ever project out the first few accepted columns from that. And so that has to be done here. So there's a couple different ways to do that. We could just collect these accepted columns that satisfy this index inequality and then do a classic Gram-Schmidt step. So again, I'm computing the R, and this would be the S vector. And this is the projection onto the orthogonal complement of this set of accepted vectors. And then I have to update the R matrix. Or we could do this like a row modified Gram-Schmidt. And that is, instead of collecting all the accepted vectors in here, I collect the rejected vectors in here. And then I do this outer product version, which is equivalent to the row version of modified Gram-Schmidt. Either of these are fine. I suspect that one is, in most computing environments, faster because you're doing matrix vector operations instead of outer products. But and there's a third bullet here that I didn't want to go into because it's just too ugly, but you can get some BLOS3 matrix multiplications by collecting the correct columns of the accepted and the rejected vectors and doing this as a matrix.
Accepted versus the rejected and vice versa.
This isn't vice versa, though. It's just two different ways of orthogonalizing the rejected against the accepted. Yeah, right. Okay, and then so here's a completely different perspective on this. So in the previous algorithm, we processed the whole matrix A. And then for any rejected columns, we have to revisit those columns. So you're visiting columns several times in this, and that's going to slow it down in many compute environments. Communication costs go way up if I have to revisit this vector every time I do a pass through the QR, the matrix for the QR factorization. So here, what we're doing is processing the columns of A using this reorthogonalization criteria given by L. And if I reject a column, I don't put it on a queue to be processed later. I just start a new block. And so this first column of Q is the first however many columns of A I process with the classical Gram-Schmidt until it tells me to reorthogonalize. And in that case, we start a new block. And so then as soon as I get to a column of A where I'm told to reorthogonalize, then Q1 is the size Q1 is going to be, and R1 is computed. And now that column of A that I was supposed to reorthogonalize becomes the first element in the Q2 block. And if I set our reorthogonalization criteria L, so remember I didn't put a 1 in there because I wanted to come back to this slide. In my code, L is a 1. But as L goes to 0, we just get modified Gram-Schmidt. And as L goes towards infinity, we get classical Gram-Schmidt. So this is a way of seeing the gray area between classical and modified Gram-Schmidt. Again, if you take L larger than 1, there's no guarantee that you have the orthogonality in columns of Q that you want. But and I haven't done this analysis, but I think the theorem that I showed earlier is going to say that I get a backward stable Krylov type method by using this classical Gram-Schmidt with the L criterion. Okay, so here is this description of how we get this QR, this block QR factorization. And I don't have a permutation this time. So this is just the first column of A, and I set the number of blocks to be 1, and the current block size is 1. And then we just process. This is a Gram-Schmidt, a classical Gram-Schmidt step here, right? Instead of using S, I used a W. But this is block Gram-Schmidt acting column-wise, right? So I have K blocks, counting the one that I'm in. And so for the first K minus 1 blocks, I'm just going to do a block Gram-Schmidt acting on a column of A. And then here, and this is what Aaron might call the inter-ortho portion for one column. And then here we're doing the intra-ortho portion, which is just a classical Gram-Schmidt step. And again, if I satisfy this L criterion, then I update my current block size. That is, I make my current block bigger. I add the current column that I'm in to the current block index, and I update this V matrix. So V stands for the columns of Q in the current block. I don't code it this way, but I thought it'd be easier for people to understand. Looking at the code, V is Q sub K plus 1, but it hasn't been called that yet. If I fail and I have to, and the criterion says you should have reorthogonalized, then I'm going to add 1 to the number of blocks. Should that be K? Yeah, and then, like I said, V was the current block, and so now I'm going to write that to Q and start a new block that just has 1 vector in it, and then it just processes column by column. And oh, I wanted to mention that, is she here? An undergraduate student here, Carolyn Jennings, did a lot of the timing results and error results on this code. She's graduating in the next few days with honors with a major in math and creative writing. And she was a linear algebra, not a numerical linear algebra, but a linear algebra student of mine who just liked the stuff. And she got a couple hours of credit, but other than that, she was just doing this for fun. Okay. So a couple days ago, somebody pulled up MATLAB's gallery and did a random SVD with geometrically spaced singular values. I didn't know that was in gallery, and I had my own code to do that, and I attributed it to Stewart. I don't know if Pete Stewart were the first one to do that or not, so I don't know if this attribution is correct, but this is a 600 by 600 matrix. It's, well, this is several of them. And so the condition number of this 600 by 600 matrix is fixed ahead of time. And the singular values are spaced geometrically. So one singular value divided by the next smaller one is constant across the whole singular value spectrum. And so what we're looking at is the number of correct digits. And so the higher, this is good going in the up direction. I'm looking at the number of correct digits in this orthogonality here. And the legend makes it seem really messy, and of course it is really messy, but I have a slide that zooms in really close here. And if you still want to zoom in on this, I'll see if, this isn't live, this isn't a MATLAB plot, this is a MATLAB plot written to a PDF, so I don't know if I can zoom in on the PDF well enough. Let's just give it a try. Oh, yeah. Oh, and but the legend's gone. Oh, there's the legend. Okay, so now we go down. We're looking at a condition number of around 10 to the 8, if we're looking right around here, right? And then we come in and I computed for n equals just 20, the mean of the error in the E matrix, I minus Q transpose Q, and the max error for several of these algorithms. Whoops. Oh, how do I, okay. I better back off. I'll zoom in on another slide, but what you can just take from here is this is essentially doing the same level of orthogonality as modified Gram-Schmidt. You can't, unless I zoom in really close, you can't even see the difference between the different plots. And the mean and the max are very close to the same, so it's very consistent. I have very little variation. And you can put your own condition number here because it's just this straight line, because I've given here the log, the condition number. So that's for a 600 by 600. Let's go back to full screen. And if, just in case people didn't believe, there's a 1200 by 1200, and then 1800 by 1800. And then here I zoomed in. So here we're looking at a condition number of 10 to the 8. Again, vertically higher is better. And you can see that the green O, and so that's modified Gram-Schmidt. So I'm not testing, I'm using that as a normal set for the experiment. And it looks like it's doing much better, and it is doing better, but look at the difference. We got like about 7.88 digits of accuracy versus 7.78 digits of accuracy, about 1/10 of a decimal digit difference in the orthogonality error here. And so it's essentially the same level of orthogonality as modified Gram-Schmidt. And here, So I was talking about the drama between the proof that classical Gram-Schmidt gives an orthogonality error as the square of the condition number of A. And a year later, a group, well, Smaktunowicz and Barlow and Langau, I think, and Langau was from the previous paper, showed that that theorem was wrong. But if you computed the norm of the S vector in the Pythagorean way that we talked about a few minutes ago, then they recovered it. And they just gave some striking examples. It was the first examples I had seen with classical Gram-Schmidt that showed it was clearly not quadratic in the condition number of A. And so I thought I'd use these same matrices that they used as counterexamples here. And so these aren't very, well, I'm starting with the 200 by 200 and going up to a 2000 by 2000, no, 2000 by 200 and going up to a square matrix. The conditioning is getting a little bit worse as you go, but this is fairly constant condition number around 10 to the 11. And again, they're about the same. This time, the algorithm where we processed all the columns of Q and then had partitioned into accepted and rejected, that's giving slightly better accuracy than the others, but again, less than a decimal digit difference in the orthogonality error. And then we applied it to a least squares problem where we computed the least squares with MATLAB \. So I think that's Householder using rank revealing QR. That's the pluses. And then this is the plain block where I'm not doing the recursion. And this is the recursive type algorithm with the permutation matrix. And then the star is the Gram-Schmidt. And again, it's all very close to each other. Here, the green line is the least squares condition number. So it's got a bit of the square of the condition number of A into it. And that's it.